That's only 200 pages.
Yeah, so last day we started talking about some of the documentation from week 1. The data sheet, for instance, is the STM32F446 data sheet. They have different names on them oftentimes, and in week 1 I tried to give you what the thing is, dash whatever it is that you go to download it on when you look at it. The data sheet is, in this one, is like 200 pages, and it talks about the particulars of, that we have how many ADCs do you have, how many DACs do you have, how many timers, and so on. The other thing that we have in the data sheet is it has a lot of the electrical characteristics. So if you go down, getting near the bottom here, you can see, so it'll tell you what VIH is, or what is the speed, all of those kind of electrical characteristics of the actual system. If I went to go and search for something like, let's see, GPIO, let's see if we close that over here, and we'll go here, and we'll go Control F, and we'll go GPIO. And so it says general purpose IOs. We're on page 37, so let's just go and look over there. So this is what it tells me about general purpose IO. Each of the GPIO pins can be configured by software as output, push, pull, or open drain, with or without pull-ups or pull-downs, as input, floating, or without pull-ups or pull-downs, or as a peripheral alternate function. Most GPIO pins are shared with digital or analog alternate functions. All GPIOs are high current capable and have speed selection to better manage internal noise, power consumption. The I/O configuration can be locked if needed by following a specific sequence to avoid spurious writing to the registers, and they can have a maximum toggling of about 90 megahertz. That's it. That's what it shows me as far as GPIOs. If I look at A to Ds, it says, hey, there's 3 12-bit analog to digital converters. That's what it tells me about them. There's another section on A to Ds that tell me what is the conversion rate and bit times and all of that is in here as well in this 200 pages. But more info on what exactly the module is like isn't there. For that, there is, in this case, the RM0390. This is all in the week 1 documentation. And it's the reference manual, RM0390 reference manual. And it says this document is addressed to application developers. It provides complete information on how to use the memory and peripherals of the 446, and constitute a family of microcontrollers, different memory sizes, packages, and all of that. And so this one is a 1,350-page document. So that's going to go more into how do I look at the GPIOs, or what more in particular is there? Yeah.
Sorry, but what does GPIO stand for?
General purpose I/O. So you just want to use it as a input-output pin.
Gotcha.
Okay. So if I go and look here, and I'll go Control F, and there's our GPIO. And so general purpose IOs, and so we'll click on that. And so general purpose I/O. Each general purpose I/O has 4 32-bit configuration registers. We looked at that last day and saw, hey, we had the mode and speed and all of that kind of type and pull up and pull down. And so GPIO, so each port has up to 16 IOs under its control. Speed selection, we looked at some of these things. Bit set and reset registers, input data register, output data register, highly flexible multiplexing. So it talks to us about all of that kind of thing. Shows you what a general purpose I/O structure is. 5-volt tolerant, so that's nice. You can get some ARM chips from different manufacturers that if it saw 5 volts, it would kill a pin. So it's nice to have the 5-volt tolerant. You can't assume that for every ARM chip that it can do that. You have to go and look. And some chips, not all pins are 5-volt tolerant. There might be some that have a few pins that cannot see that. So you always have to go and look when you're going to put something other than the 3.3 volts up. Okay, and then it goes into some of the configuration things that we've gone and looked at. Talks a little bit about some of that. Alternate functions. So on a pin, for instance, it says here is a pin 0 to 7 and pins 8 to 15. Here's a bunch of different functions. It says for pin 0 to 7, the GPIO X, where X being, port A, B, C, D. There's alternate functions, so timers or I2C or SPI or CAN bus or flexible memory controller, quad SPI. So it has a whole bunch of things that we can put on the pin. And then it depends on what I need. So I could say alternate function and then use SPI on it or use it as a timer output or do that kind of thing. Serial peripheral interface. And so just different things to communicate. So we'll be looking at some of these. I/O bitwise handling. The bit set reset register is a 32-bit register, which allows the application to set and reset each individual bit in the output data register. In other words, I could go and toggle a single bit on there. And so the big thing with this is it has a lot more detail than the 200-page data sheet. The 200-page data sheet will give us some information, give us electrical characteristics. If I'm wanting to interface something, I would go and say, what's the maximum that I can put on a pin? What's the current sink and source? All of that is in that 200-page sheet. More about what some of these how things are configured with an I/O port or with an A to D converter or what have you are going to be found in this 1,300-page reference manual. I also then, so I would look at this, I also have the HAL user's manual. It's again in week 1. And the HAL user's manual is 1,800 pages. And the HAL user's manual, hardware abstraction layer, it is the API, the application programming interface manual for how do you talk to it using the C compiler. How do you go and talk to the individual things? So I would look in here for the functions, and when you go with IntelliSense, I said type in HAL and go control space, and it brings up, oh, HAL GPIO control space. Here's the things that you can use. It's documented in this. Okay, so you would go, what does HAL GPIO write do? It's in this. It will tell you how to put all of that kind of information in there. The reference manual shows you about the port and how things are configured in the individual registers, and this says how do you use the C libraries and programming interfaces to go and talk to it. So again, if I go Control F, and so I go to GPIOs, so there is my GPIOs. So GPIO HAL APIs are the following: HAL GPIO init and dinit, HAL GPIO read and write, and HAL GPIO toggle. Now, when we use the graphical interface, the Cube IDE, to go and select our pins and say I want me to have a general purpose I/O to either be an output because I'm attaching a LED to it, or be an input because I'm going to attach a button to it, then this is where I would go look at how do I select it. By default, when it went and initialized everything, the button B1 is going to be set up on an interrupt. You could use an interrupt. We haven't really talked about interrupts, so I just expected you to take B1 and set it to an input so you can have HAL GPIO read to go in and read it. We are going to deal with interrupts and all sorts of other things coming up, but I don't want that to get ahead of ourselves with this. Now, some of the functions, it says you need HAL GPIO init. When I selected pins as inputs or outputs, as part of the cube ID generating initialization code for it, it calls that. You can actually see it calling in main. It will call HAL init to initialize this whole HAL system. It calls setting up the clocks. And if I did anything with GPIO ports, it calls HAL GPIO init. It already did that. It's documented here because you didn't have to use that. You could use HAL, but not use the cube IDE and write it all yourself. And what it's saying is, if you want to use any of the GPIO functions, you had to call HAL GPIO init first, okay, to be able to go and set all of this up. And so it has done all of that. So if I scroll down a little bit, gives us some of the options. I can go GPIO speed low, medium, fast, fast, high, for instance. It says configuring GPIOs. You could go GPIO pin 12 or 13 or 14 or 15. And the reason for that is because when you go and are setting things up in a structure, it has a 16-bit I/O port, and so it's looking at each of the pins. So if I have 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, then what it's going to do is say, when you call the initialization for GPIO, it goes and says, hey, when you want to look at it, we did 15, ORed with 14, ORed with 13, ORed with 12, so this is what we get. So when the initialization function is, because I'm setting pins for LEDs or all outputs, it looks at where there's a 1, and it says, configure those pins for outputs or inputs or whatever you did. Last day we had a look at how we set up the structure for the actual GPIOs. Okay, so that's where we see this. It then has, we'll talk about the interrupts and things like that coming up. So let me go to, Control F. Let's go now. GPIO. Hopefully. I should be able to. So scrolling down, I wanted to find out about one of the IntelliSense things that I did was HAL GPIO write. What exactly is HAL GPIO write? And so I can click over there, and it says HAL GPIO write pin, and it says the function is HAL GPIO write pin, and it says we have a port, and which is going to be a 16-bit number, and we also have a pin and a pin state. So it says GPIO-X, where X can be A to K. In other words, is it GPIO-A, which is general purpose I/O port A, or B, or C, all the way up to K, depending on if I have a chip that has the full number of ports. And then the pin says it can be anything from 0 to 15, because it's a 16-bit port. We have a 32-bit microcontroller. It has 16-bit ports. Your PICs had an 8-bit port and an 8-bit microcontroller. And pin state, it says pin state can either be GPIO pin set or reset. And so if you go and look, that's just an enumerated type to zeros or ones. Okay, so I have a reset. It's just making it a 0. And so that's telling me about it. We also, in the IntelliSense, when we selected that, you have HAL GPIO toggle pin. And so again, it says toggle pin. You have GPIO X and then pin. So I can put a port name and a pin name and just toggle. So it'll automatically, if I just didn't want to go HAL write and set it, do a delay, HAL write and clear it, and do a delay and do that, you could just go HAL toggle and it would keep track of it and toggle it. That was one of the options that are on there. And so I know that because I'm looking at this. And again, I said, hey, I've had some of you go, oh, let's say it's on port B, pins 15, 14, 13, or what have you. And so you could call it GPIO-B, and then you could call it just pin 15, for instance. And so you could do that, or, well, actually, the bit 15. And so you could do that. I said, hey, when you go and name your pins, and the reason for naming your pins is it abstracts it from the port. And so in my IDE, let's open it up. And my default workspace.
How was the time set with that toggle?
Oh, the toggle will, as soon as it hits that, it just toggles. You need a HAL delay.
You said
Yeah. Yeah, it's not going to go separately and do it or anything like that for sure. Let me just go close.
oh, so it's just gonna flip the state.
Yeah, it just flicks the state. That's all it does. Okay. Yeah.
Is there any measures that can just toggle what person to like setting or resetting the pin?
If you're just wanting to flash a light, toggle's great. But if you want more control over it, then you can specifically just say, I want to write something, I want to clear something. When we set up things, for instance, when we set up our TFT, you're going to be needing to enable a chip select line and be able to pull it high and low, and at different times you would use the sets or the clears. If I just had a light blinking, I'd just use toggle. So over on, for instance, this example, I have PB15 and it's red lead, and so I highlight over that, and if I click, I had set it to GPIO output, for instance, and then let me right click and enter user label, and it's red lead. So when I did that, when you generate it, and if you don't, it'll just know it as GPIO 15, okay? If you do that, then it will put in main.h the association between your label and the port. And the nice thing about that, so if I go over to, let's go over to core, which has all my code in it, and source, and we look at main.c, one of the things that main.c has is main.h, and that, of course, is over in the includes. If I can click on it and double click main.h. But let's say I didn't know where it was. One of the things I could do is I could just highlight this main.h, and I could right click and I go open declaration, and it should open it for me and take me there. So if you didn't know, some of these things are buried in a lot of directories and sometimes it's hard to find. Highlight the thing and go open declaration, and it should take you to it. Okay, so here we scroll down through, and it has, I said red lead, so there's red lead right here. So here's red lead is a GPIO pin 15, and we looked last day, GPIO pin 15, it was 0x, it highlighted pin 15. That was the only one in the 16 bits. So pin 14 was 0, pin 15 is 1000, pin 14 is 01000. And so by ORing them, that's where we got what I showed on the board, where they're pin 15, 14, 13, or 12 are ORed all together, because when you call that structure, fill in that structure with it and call the initialization for the structure, it's going to do things on all of those different pins. Red lead GPIO port is GPIOB, and I could have used GPIOB, but if I use GPIOB and it's all throughout my code, then I need something. There's a lot of things that are on alternate functions on pins, and if you had need for it for something else and you needed to move your LEDs to another port, then you just move them graphically, still call it red lead, put it on any other GPIO pin, say it's an output, regenerate your code, and all it did was just change in main.h what it's pointing to. Okay, your code still dealt with red lead and red pin and all of that. Okay, so it's a nice way of abstracting things and making it easier when you're maintaining your code. Okay, so where are we here? Going back. Okay, so we had toggle pin. One of the other ones that we had then was if I go and say, where was it? Where's my read pin? Read pin. HAL GPIO read pin. So it says it wants a type and a pin, and so it says it's GPIOX, or it can be one of the one's input return values, the input port value. So if I go back over here, so HAL GPIO read pin, so let me go back over here somewhere, and let me go down into see, here's our HAL initialization, our system clock config. There's that GPIO init. The HAL documentation said you had to call before it does some of that others. It's already set that up for you, initialized the pins to inputs and outputs in the way that you wanted graphically. And then I had a HAL GPIO write. If I do a HAL GPIO, for instance, and I go and look at which one's the read pin. So if I go read pin, it highlights and it says GPIOX. So whatever port that is, I don't know where that button is, whatever port it happens to be. I do remember it was called B1, I think, B1. So I'll go B1, control space, and then it says, oh, well, I got two B1s. There's port and pin. And so I'll go port, and then I can tab over, and it goes, okay, what's the pin? And I go, again, I know it's B1, control space, port or pin, and then there we go. And there's my HAL GPIO read. Okay, so that's going to read the button. Now it's going to read the button, and it returns the button value, and then it's going to throw it out because I don't assign it to anything. So you either assign it to a variable, or you wrap it in an if statement to do something with it. Okay, if you just temporarily need the value. So if I just put that in an if HAL GPIO read pin, so I could do something like that, and I could go if HAL GPIO read pin, there, let's do that, do something. If it returns a 1. But I wanted it to be, I wanted to do something if it's a 0. So what do I do there? Yeah, so you could go there, and you could go equals 0. Or I could go not, because if it's a 0, it's a 1. If it's a 1, it's a 0. Okay, so you could do something like that. Now, if you had need to keep it, then I would have to do something like, instead of having that, I might want to go int my button equals that, and then do something else, do if my button down below. Let's do that. So you could do something like that. Yeah, and then
If you wanted to put this all just in like a separate function, how would you do that?
And you just do like if my button. So if you wanted to put a separate function somewhere else,
yeah.
So if you're writing separate functions, let me just get rid of that. If you're writing separate functions, this is main. Okay, you have to have, so main starts here and it's going down to here. So you have to have your functions outside of main. Now there's a couple of places that it will let you put it where it won't wipe out. And so you could put things in user code begin and end 0 above main and declare a function that you can then call in main, and because it was declared before you used it, it will exist. So you could put it there. The other thing that you can do, and where we'll put a bunch of things, is down near the bottom. And so I have, and we'll be looking at that as soon as we do come up to A to D's, And so way down after all of this initialization stuff before the error handler is user code begin and end 4. So I could put something there. But if I put something there, it's declared after you could use it in main. So it will say what's going on. So you need a prototype. I wish there was a place I could put prototypes. And so you go up to, I can do that here. And so if we look at user code begin and end includes, that's where your includes are. Your own type defs, your own private defines, your own private macros, your own private variables, your private function prototypes. So if you declare something in user begin and end 4, then stick its prototype, copy the header of it, and put it there. Yeah.
Can we make just like a separate header file like you're doing?
Oh, absolutely. And so if you everything put in a separate file, and so what you would do is you would go over here and you would say, hey, I want a new source file. And so you have a new source file and call it, let's call it thermistor.c. So you have a thermistor.c, and then the prototypes go in thermistor.h, set aside, for instance, here. We're going to be doing this real shortly, talking about lab 3. So, and you would put one in there. So you would have a whole separate file. So I have a separate C and a separate H file. That's awesome. But then I need to reference it. So in main, you go and say, where are my includes? You include, if I have a thermistor.c and a thermistor.h, you have include thermistor.h right there.
And C the definition.
Yeah, H is the prototype and C is the actual code that is going to be coming in. Yes.
Yeah.
Okay. And so we're going to do that. Okay, I'm going to show you coming up for when we start doing the next lab. Yep.
If you want to go back to the where you can change the pins, like what if it's input, output, whatever it is. If it's not popped up like that, how can we open it?
If this isn't open?
Yeah.
So let's close this. And so you are looking down here at the IOC file. And so this is called week1.ioc file. Now, I double click it, that's going to open up. But let me just go and I'm going to say open with a text editor. It's just a whole bunch of text describing what that graphical system is all about. Okay, so it actually looks at that and says, okay, somewhere in here I've got a red lead. GPIO, there's the label is B1 and it's the blue push button, you know, all of that kind of stuff.
When I changed it to input, it changed the name of the actual pin.
Yeah, so when you...
So I just kept it as that name.
Yeah, that's fine. Yeah. So it's just changing the name. It's going to reference it in the main.h file as to what you want. You may not want it to call it B1. So in here, for instance, I said, hey, the default, if I highlight over it, it says blue push button is GPIO external 13. So it's an alternate function it's using. And so let me just click on it. It says GPIO external 13. So by default, it's set up not as an input, but as an interrupt. And so I will go to an interrupt service procedure. I'll show you about how all of that works down the road. I said, hey, really, it would be good right now if instead of that, we just made it an input. So we can make it an input. And as soon as you change something with it, it just says, I'm an input. And so what I want to do here is I want to right-click, and in here, enter user, and it was called B1 before, so just keep everything the same. There, B1, or blue button, or whatever you want to call it. That's how I would reference it. How GPIO blue button, or how GPIO B1, or what have you. Okay? And so any of these kind of ones, I would do that. If I look at PA2, highlight over it, it says, I am USART2 transmit, mode asynchronous. So we can have synchronous data, so SPI, I2C, things like that. Or we can have asynchronous, in which case it's like our standard RS-232 type UART. And so this is, again, by default, these are connected up to our ST-Link, and it has a virtual COM port that will give us access to that. And we can have a look at that down the road. But if I click on one of those, for instance, it says it's UART to transmit. If I look at this, this is going to be UART to receive. So it's an alternate function. It's not using the general purpose IOs. Okay. All right. So back over to, where are we here? So, you know, if you use any of the functions, it tries to tell you what it wants. And so this documentation goes, and if you need to know, for instance, how many parameters, I've had some people look at the read pin, and you go, okay, well, how many parameters? It tries to help you when you put it in and do IntelliSense to say this is what it's looking for. The other thing is when you do it is if you highlight over it, it tries to tell you as well. Let me go over here and go to here, and let's go down to, where is my right pin? So if I highlight over the right pin and I click into it, it says, hey, sets or clears the data bit. This function uses the bit set reset register to allow atomic read write. GPIO X is where X is A to K, which is the port, and then GPIO pin is the pin parameter GPIO pin X, where X is 0 to 15. So it's expecting me to say GPIO pin 0 all the way to GPIO pin 15 to get like what we put on the board. So just by highlighting over it, it'll pull it up. And then if you needed parameters for set or reset, then it's saying, okay, this last one here could be a pin reset or pin set, and so it could be one of those. Now, if I go over to here and I highlight that, it says set is 1. Somewhere it is enumerated as a 1. Okay, it has set and reset somewhere in the system. If I go, I wonder if it'll let me do that. Let's open declaration. There's the enumerated. There's where it's, so it defines a type, GPIO pin state, and there's 2 values, starting at 0, 0, and 1. That's where they are. Okay, in STM32F4 HAL GPIOH. Okay. Right, look at the read pin. It says, hey, again, GPIO port, GPIO pin, that's all it has. And I can go and look in the actual code here, and it's saying return bit status. So it's going to return a GPIO pin state, which is going to be bit status. So doing this, it returns a value, and so on the read. And so if I want to keep that value, then I have to either put it in that, or if it's just temporary, put it in a switch statement, or put it in an if, or a while, or what have you, and it'll just directly use that. Okay. So let's go back to here. So combination of your data sheet, your reference manual, and your HAL is kind of what you'd be going back and forth with to see what you need to accomplish some of this stuff. Looking at the data sheet again, I want to go to we looked at it the other day. It's, I think, page come on, where are you? I think I must have missed it. I think it's in around page 15. There. 16, page 16. So this is what I like to reference in the data sheet, the 200-page data sheet. And we talked a little bit about it last time. This whole thing is the black chip that you see. But in it, the ARM Cortex is a small piece, and the rest of it is, and so that's what ST licenses off the ARM Corporation, that piece, and then they can stick on their silicone whatever they want. How many ports do they want? Do they want timers? All of that kind of stuff, and it will talk to this Cortex, in this case the Cortex M4. Some of the other things that are in this part of the silicone is JTAG and software debugging. So that's the interface from this chip to the ST-Link chip. And there's also a software debugging end. There's a back channel with that part of the silicone attached to the M4 to actually get data values from variables in real time when your system is running out to some other monitoring system. We also have floating point unit. The external trace macro cell ETM is again about the debugging, and nested vector interrupt controller, NVIC. We're going to start looking at interrupts coming up. We've got a bunch of things to do with ADCs and polling and interrupt and DMA. The nested vector interrupt controller is another piece of silicone attached that looks at all of the different interrupts that are possible and feeds to the ARM the next interrupt to service. So the ARM just goes, what do I need to service? It doesn't worry about priorities, all that kind of stuff. That NVIC, you set it up and it does it, okay? And then again, we're on a bunch of different buses, and coming off the Cortex, we have our RAM, we have our flash. Because of the chip that we have 512K. There are some that give you 1 meg in this family, and you can get 2 meg on some of the other families. And then there are different interfaces. For instance, in our addressing, 32 bits, we have a 4 gig of address space that we can go and attach things to. And we'll have a look at the memory maps. But we could attach external flash, external static RAM, a TFT screen in that kind of fashion as well. And you could put it in your memory map in a certain location and directly address it. And that's what all of this stuff is available for. We also have a camera interface, USB interfaces as well that go to the different buses. Advanced High-Speed Bus 2 goes at 180 megahertz. Same with Advanced High-Speed Bus 1. And so there's all of these other modules that are on there. We talked last day about all the different ports you could have up to port H. And again, those go to this Advanced High-Speed Bus 1 with the different clocks. And there's a bunch of timers. This is a real-time clock module. And so I can actually set it up and with a battery backup, have this thing running, keeping track of time. You can set things up like wake up once a year, wake up every day at 8 a.m., do all of that kind of thing. And it has, on board, you have a 32.768 kilohertz crystal on the Nucleo board to take advantage of that. By default, they don't have the battery and things there. There's a VBAT pin. You can hook an external coin cell to it and go and set all of that up. I have had the guys in the back room order this board. So there maybe next week, end of next week. So I wasn't going to do it because this I put together just in the summer to try and make it easier and have less wiring and all of that kind of stuff. And I want to change some things with it and put Wayne's board on it as well and a few things like that. And so I'm halfway through doing that, but I went, let's just run it and just give you a board. So if you guys want to just plug your LCD in and not have to do a whole ton of wiring, hopefully those boards will be back, in about a week, and you can do that. So should be back in plenty of time before we have to wire up the displays. Yeah, but it's not by any means a perfect board. It's just my prototype. And so anyway, we have all of the timers and UARTs and all of this kind of thing that are available. This whole thing, when you go to the IDE, because you said it's a 446, it knows about where those things are. Because you said it's a Nucleo, in addition to knowing about what your chip is, it also knows what other peripherals are on board. we have a button and a light. That's kind of what we have. But some boards have all sorts of things. They have accelerometers on board. I have all sorts. And if you say you want the board, it configures all of your board, not just this. It's easy to do on this one because the only thing we have is, like I say, we have the LED, which unfortunately isn't in a place I like for what I want to do with some things, but that's okay. For the first few labs, we'll just use it. It has our UART channel for our debug, and we have our button. That's going and talking to our crystals. And this, and this are to do with our debug. And so we'll talk more about those as they come along. Okay, so we're going to reference the week 1 stuff. You have a picture of the Nucleo board where the pins are. You have the data sheet, the 200-page data sheet, to kind of give you that picture we just looked at of where the arm is and where all the different things are. It was more important before because you had to go through and look at the buses and turn on the appropriate bus clocks in order to make everything work. Now it just sets it all up for you and says, I don't know what you want to do with the ports, but I'll make sure that they're all ready for you to use. When we go to set up an A to D converter, I don't know what you want to do with it, but I'll set it up so it's all ready to go. So we can go and set up the A to D converter. That brings me into hopefully a segue here. I was saying what's happening into next week's lab. So next week, what we want to do is use an ADC, an analog to digital converter, and we want to connect it to the Kuman thermistor. Okay, so from your parts kit, I have some if you've lost the thing or whatever, but try and find your parts from your Kuman kit. And so we have a thermistor, and we want to connect it to PA1 on the Nucleo board, okay? And so you're going to make a new project called ADC Pole, and we're going to connect up your thermistor to PA1. I got to update that one. It says, write a program to configure the ADC to read the thermistor in single conversion mode, display its ADC value in decimal and its representative temperature to 1 decimal place to the SWV ITM console using printf. Upload a screenshot of your debug workspace showing the thermistor raw values and equivalent temperatures. Okay, so there's a whole bunch of questions that we have to figure out. One, how do I set up the ADC? I have no idea what SWV is. I don't know how a thermistor works. There's a few things like that. So we need to talk about some of those things. The week 3, if you look in D2L under week 3, there's a whole bunch of documentation for some of these kind of things, and we will go into it. One of the things I'd like to point out, so it says PA1. So let's go over here, and I want to find where PA1 is. Oh, there's PA1. So if I click on it, what would you pick? ADC. Now you could pick, and don't, but you could pick GPIO analog because it's an analog to digital converter, so pick analog. But there are other analog things there. That's not the one you pick to use the ADC. Okay? And you can select analog and select ADC, which will make things not work for you. It will let you select those two things together. Okay? So just select ADC. But okay, what ADC do I pick?
First one.
Sure, let's pick the first one. There are 3 A to D converters on your chip. Some have 2, some have 1. This has 3. You have 3 separate A to D converters. I could have 3 running independently on different channels, grabbing data at the same time, doing the conversions and things. In fact, you can set it up so on one input, you could set it up so one grabs data, so it's sampling. As soon as it's ready to go and read the data, turn the other one on to the same input, then turn the other one on, and improve your sampling rate by using 3 different converters. We're not going to do any of that, but we're going to just look at one of them. But you could then say, I've got a potentiometer over here, I've got a thermistor over here, I've got something else over here, and use the 3 of them independently. Okay? And so We have all sorts of different ways. We can use just one and have up to 16 channels and have it read all 16 different inputs of some sort. One A to D converter cycling through the channels and reading all of them. Yep.
You have to set like a separate cells for the
Oh,
EDC.
oh yes.
Okay.
Yes, we're going to have to do all of that. So I want you not to pick analog because that's, you go, yeah, it's analog. Just pick ADC 1 input 1. Okay, and then we'll configure some of the other stuff. So by selecting that, so let me just do that. Let's go A to C input 1, and then I'm going to right click and I'm going to enter the user label and I'm going to go thermistor. Okay, so there's thermistor. And so over here under analog, ADC 1, then there's input 1, then there's a whole bunch of configuration. It's set on NVIC here, but let's see, I don't know, parameter settings. So if I go to parameter settings, then it says, okay, here's some settings. Now, most of the thing is default. It says clock prescaler, resolution 12 bits. If I click, the more bits, there's a time per bit that it takes to do a conversion. If you need it to be as fast as possible, but not as accurate as possible, then you could go, I just want 6 bits. It can do it in 9 clock cycles. But by default, we're just going to leave it. It's 12 bits. It takes 15, takes whatever the number of bits plus 3 in order to do the conversion. Okay, so we'll go and convert that. And so just leave it as the default. But you can change all of these things. There is a structure that is defined when we set up the ADC, and then we do all these selections. It fills in the structure, and there's a HAL ADC init, which takes the things we filled in the structure and sets up the ones and zeros, just like we talked about with the GPIO port. Okay, and so there's that right alignment. It is a 12 bits. We're doing 12 bits, and so it will return things in the right most 12 bits, or it could be in the leftmost. Okay, we have a 16-bit address that we're going to get data from. Scan conversion continuous. We're going to have to talk about all of that kind of stuff coming up. If you look at rank, it says number of conversions 1. We only have one thing that we're converting. We could have 16 channels. And if you have 16 channels, it wants to know what order do you want things done in. And so it will go through your ranking and say, I'll do this one first, this one next, this. You could have 3 A to Ds, each one with 16 different channels, all running at the same time. Okay? And so on this one, we're saying the rank. So if I expand rank, where did it go? Where'd it go? Oh, no, I didn't expand rank. I got rid of it and said, no, just do one. Okay. There we go. So, not injected. Number of conversions 1. Rank. Okay. So, if I expand the rank, it says regular conversion, external trigger, num, rank, channel 1. We were on channel 1. And so sample time. And so if I had multiple channels, the rank is the order I want to do them. If you had multiple ones, it would say, okay, here's channel 1, channel 2, channel, whatever. And you could say, which one do you want to do first? Sample time, 3 cycles. Let's give it a little bit more time, something like 84 cycles. But that's where you change all of this stuff. Yeah.
So on a single channel can be one sensor or one.
Yep.
Sensor.
Yep.
You can have, on one pin you can have 16.
One pin is one input, but I can have on one A to D converter going through 16 different pins on your chip. So I can then say on the one A to D converter, I can say, here's all the different pins that I want you to read. What order do you want to read them in? And it will go through in order. It will change over to the different pins to the one A to D converter.
And you can just use GPIO.
So when I highlight, see there's PA7. Some of them have it, some of them don't. This is ADC1 input 7.
Okay.
So you select where you want these things to be. we got lots more to talk about with the ADCs. This is just a preview for next week's, but there's that's the start, and we'll talk about a lot more next time.